In this video, we will talk about the chain rule. What is the chain rule? And how do we even know when we need the chain rule? It is used to find the derivative of the composite function. It is more complicated function never had any rule before to find. For example, 2x cubed plus 1 to the power of 10. This is the composite function. It look like a normal function, but it is complicated. For the previous rule, we can only find the derivative of 2x cubed plus 1 and x to the power of 10. But we don't have any rule to find the derivative of the function like this. We can find the derivative of 2x cubed plus 1. Derivative of 2x cubed plus 1 is 6x squared. And we can find the derivative of x to the power of 10. Derivative of x to the power of 10 is 10x to the power of 9. Right. But, what is the derivative of 2x cubed plus 1 to the power of 10? Let's find the way. Okay, if we have two function f and g. The composition of f and g is f of g of x, let y equals f of g of x. We can say, f is the outside function, and g is the inside function. So the derivative of this function, dy by dx is. We take the derivative of just the outside function first. And leave the inside function alone, don't touch it. And after that, we multiply by the derivative of just the inside function. So, the derivative of f of g of x is the derivative of the outside, f prime of g. Multiply by the derivative of the inside, g prime of x. On the other way, if we have the composite function, y equals f of g of x. We can let g as a new function u, then u is the function of x. We can find du by dx, and equals g prime of x. When we let u as g of x, then, y will be the function of u. And we can find dy by du, that is f prime of u. Okay, from dy by dx is f prime of g, times g prime of x. The other way would be, dy by du, times du by dx. Okay, let's solve our problem. Find the derivative of 2x cubed plus 1, to the power of 10. Look at this function, the inside function looks like 2x cubed plus 1. And the outside is the inside to the power of 10. We can let the inside function be u equals g of x and equals 2x cubed plus 1. And the outside function will be f of u equals u to the power of 10. So the derivative of f, u to the power of 10, with respect to u, or f prime of u is 10 times u to the power of 9. Plug in u equals 2x cubed plus 1, we have 10 times 2x cubed plus 1, to the power of 9. And du by dx or g prime of x is the derivative of 2x cubed plus 1, which be equal to 6x squared. Then, the derivative of 2x cubed plus 1, to the power of 10 is f prime of u, times g prime of x, would be equal to 10 times 2x cubed plus 1, to the power of 9, times 6x squared. And then to simplify, 10 times 6x squared, is 60x squared, times 2x cubed plus 1, to the power of 9. Okay, let's take a look at another example. If y equals square root of x squared minus 1, we can see that it is not only the square root of x, it is the square root of the function of x. So it is the composite function, we need chain rule to find its derivative. Before finding the derivative, we need to rewrite the square root to be the power function, which is power 1/2. Then our function is x squared minus 1, to the 1/2 power. We can see obviously, the inside function is x squared minus 1. Then dy by dx is the derivative of u to the 1/2 power, which is 1/2 times u to the power 1/2 minus 1. Which is 1/2 times x squared minus 1, to the power of negative 1/2, 1/2 minus 1 is negative 1/2. And then times du by dx, the derivative of x squared minus 1. Derivative of x squared is 2x and derivative of 1 is 0, so it would be 2x. And then simplify this function, we have x divided by square root of x squared minus 1. Next, if y is equal to 1 divided by x squared plus 3x plus 1. Actually, to find the derivative of this function, we can use the quotient rule, low d high minus high d low over low low. But if we move the bottom up to be the power function, it would be x squared plus 3x plus 1. To the power of negative 1. So it look like u is x squared plus 3x plus 1, then it is u to the power of negative 1. So dy by dx is the derivative of u to the power of negative 1, which is negative 1 times u to the power of negative 2, right, negative 1 minus 1 is negative 2. Or x squared plus 3x plus 1 to the power of negative 2. And then times du by dx, the derivative of x squared plus 3x plus 1, which is 2x plus 3. And finally, when we simplify, moving the negative power to the bottom, it would be negative 2x plus 3, divided by x squared plus 3x plus 1, square. Look at this example. If x is the demand function, depends on p, the price per unit, and given by 98 divided by square root of 2p plus 1, minus 1. Square root of 2p plus 1 is the composite function, we need chain rule. Rewrite to be the power function, 98 times 2p plus 1, to the power of negative 1/2, minus 1. Find the rate of change of the demand with respect to the price p, when p equals 24. Okay. The rate of change of the demand with respect to the price, is the derivative of x with respect to p. Follow the chain rule, would have negative 1/2 times 98, is negative 49, times 2p plus 1, to the power of negative 1/2 minus 1 is negative 3/2, and then times the derivative of 2p plus 1 which is 2. And the derivative of 1 is 0. So we have only this. And then simplify it, and would be negative 98 divided by 2p plus 1, to the power of 3/2. When p equals 24, plug in 24 to x prime of x we have, 2 times 24 plus 1 is 49, and 49 to the power of 3/2 is 343. Finally we have negative 2 over 7, which is the negative number. So if the derivative is the negative, it means that the function is decreasing. So for this function when the price is $24, the demand decreases at the rate 2 over 700 units per dollar. Look at the graph of this function. It decreases when p increase. It makes sense, right? When the price increases, we can produce the product decreasingly. The next topic is the higher order derivative. What is the higher order derivative? Suppose we have a function, y equals f of x. So dy by dx is f prime of x, this derivative is called the first derivative. And the first derivative still be the function of x. We can find the derivative of the fifth derivative again. d by dx of dy by dx or f prime of x, prime. Then the notation will be d squared y by dx squared, or f double prime of x. And it is called the second derivative. And also, the second derivative is the function of x. We can continuously to find the derivative of the second. d by dx of d squared y by dx squared, or f double prime of x, prime. And the notation is d cubed y by dx cubed, or f triple prime of x. And this is called the third derivative. And again, if we find the derivative of the third, it is the fourth derivative. Or d to the fourth by dx to the fourth. But another notation, we use the number in the brackage instead of prime. So it is f to the fourth derivative of x. And so on. Higher and higher derivative. The n derivative is d to the n by dx to the n or f to the n derivative of x. For example, if we have the function like this, the first derivative, dy by dx, is, derivative of 4x to the fifth is 5 times 4, is 20, times x to the fourth. Minus derivative of 5x to the power of negative 2, is, negative 2 times negative 5, is plus 10, times x to the power of negative 3. And plus the derivative of 2x to the power of 7 over 3, which is, 7 over 3 times 2, is 14 over 3, times x to the power of 4 over 3. And plus the derivative of 3x, which is 3, and minus derivative of 9, is 0. So this is the first derivative. For the second derivative, d squared y by dx squared, which is, derivative of 20x to the fourth, is 4 times 20, is 80, times x to the third. Plus derivative of 10x to the power of negative 3, is negative 3 times 10, is negative 30, times x to the power of negative 4. And plus derivative of 14 over 3 times x to the power of 4 over 3, is 4 over 3 times 14 over 3, is 56 over 9, times x to the 1/3 power, and derivative of 3 is 0. And the third derivative, d to the third by dx to the third, is, derivative of 80x cubed, is 3 times 80, is 240, times x squared. minus derivative of 30x to the power of negative 4, is negative 4 times negative 30, is 120, times x to the power of negative 5. And plus derivative of 56 over 9 times x to the 1/3 power, is 1/3 times 56 over 9, is 56 over 27, times x to the power of negative 2/3. What is the meaning of the second derivative in the business? If the first derivative is the marginal, the second derivative would be the marginal of the marginal, or the rate of change of the marginal, or the fast of changing of the marginal. The fast of changing is the derivative. Then the fast of changing of the marginal is the derivative of the derivative, which is the second derivative. If the revenue from the sale of x units is given by R of x equals 100x minus 0.01x squared, find the instantaneous rate of change of the marginal revenue. Because the marginal revenue is the first derivative R prime of x, so the instantaneous rate of change of the marginal revenue will be the second derivative R double prime of x. Then to find R double prime, we have to find R prime first. Then R prime of x is the derivative of 100x minus 0.01x squared. Derivative of 100x is 100, derivative of 0.01x squared is 2 times 0.01, is 0.02x. So R prime is 100 minus 0.02x. Then find R double prime. Derivative of 100 is 0, and derivative of 0.02x is 0.02. So R double prime is negative 0.02. So the instantaneous rate of change of the marginal revenue decreases at the rate 0.02. In this topic, we will apply the derivative to solve the problem in business. In business, we talk about the cost, revenue, and profit. When we buy some goods for business or produce some product, we need to pay as least as possible. That means we need the minimum cost. And then when we sell our product, we need the maximum revenue, and maximum profit. Well, cost, revenue, and profit are the functions. So, we will learn how to find the maximum or minimum of the function. Let's take a look at a scenario. On vacation, you make a hill trip with your family, you drive your own car. When you drive your car up to the mountain, sometimes you are going up, and sometimes you are going down. Going up and going down. When you are going up and then going down, you pass through the top of the hill. And when you are going down and then going up, you pass through the valley of the hill. When you are going up to the top, it looks like you are increasing. When you are going down to the valley, it looks like you are decreasing. Increasing and then decreasing, you pass through the local maximum point. Decreasing and then increasing, you pass through the local minimum point. When we are going up, we say that the function is increasing. The slope of the function is greater than 0, or is positive. When we are going down, we say that the function is decreasing. The slope of the function is less than 0, or is negative. Increasing, the slope is positive. Decreasing, the slope is negative. When the function is increasing, the slope is positive. And when the function is decreasing, the slope is negative. When the function is increasing, and then decreasing, it passes through the top of the function. When the function is decreasing, and then increasing, it passes through the valley of the function. At the top or the valley, the slope of the function is 0. Or sometimes it does not exist, if the top or the valley is a corner, or vertical tangent. Then when the slope of the function is 0 or does not exist, it occurs at a critical value. If f of c is defined and f prime of c equals 0 or does not exist, c is the critical value. But if f of c is undefined, c is not a critical value. Let's consider this graph. This graph has 8 critical values. At which critical values, f prime of x equals 0, can you guess? Yes, it is at C1, C2, C4, C7, and C8, right? And what about at C3, C5, and C6? They are at which f prime of x do not exist, right? At C3, it is the vertical tangent, the slope is infinity. At C5 and C6 are the corner the slope do not exist. And we can see the graph that the function is increasing and decreasing. When the function is increasing and the decreasing, it passes through the top of the function or the maximum point of the function. So the maximum points of the function are at C1, C4, and C6, right? Because the function is increasing on the left and decreasing on the right. When the function is decreasing and the increasing, it passes through the value of the function or the minimum point of the function. So the minimum points of the function are at C2, C5, and C7, right? Because the function is decreasing on the left and increasing on the right. So what about at C3 and C8? The function is increasing on the left and increasing again on the right. So they are neither maximum nor minimum. When the function is decreasing on the left and increasing on the right, it is passing through the relative minimum, or sometimes we call the local minimum. When the function is increasing on the left and decreasing on the right, it is passing through the relative maximum or the local maximum. The relative maximum or minimum occurs at the critical value, where f prime of x equals 0, or does not exist. To find the relative maximum or minimum, we will solve the equation f prime of x equals 0, or does not exist. Then we will get the value of x, so it is the critical value. And then we will identify the relative maximum or minimum at this critical value, by considering the slope or f prime of x on the left and on the right are positive or negative. If the slope on the left is negative, the function decreases. And the slope on the right is positive, the function increases. Decreasing on the left and increasing on the right. So there is a relative minimum at this critical value. And if the slope on the left is positive and the slope on the right is negative, the function is increasing on the left and decreasing on the right. So there is a relative maximum at this critical value. Suppose we have the derivative of the function f prime of x equals x times x plus 2 times x minus 2. It is a product of three linear factors. We let the derivative equals 0 to find the critical values. We will have three factors equal 0, x equals 0, x plus 2 equals 0, and x minus 2 equals 0. And solve these equations for x. We have x equals 0, and x equals negative 2, and x equals 2. And they are the critical values. And next we need to know the slope on the left and on the right of each critical value is positive or negative. We can put them on the number line from low to high. From low to high, we put negative 2 here, and put 0 here, and put 2 here. Now three critical values divides the number line into 4 intervals. To determine the slope on each interval is positive or negative, we can pick up one number on that interval and plug into f prime of x. Okay, on the interval from 2 to infinity, x is greater than 2, we can pick 3, and plug into f prime of x. So f prime of 3 is 3 times 3 plus 2 times 3 minus 2, which is 3 times 5 times 1, and equal to 15, it is a positive. Actually we don't need to know the value, we just need to know it is positive or negative. Or we can consider like this, 3 is positive, 3 plus 2 is positive, and 3 minus 2 is also positive, then positive times positive is positive. So that means, on this interval the slope is positive, the function is increasing. On the interval from 0 to 2, we can pick up number between 0 and 2, for example we can pick 1. And plug into f prime of x, and we have here, equals negative 3, it is the negative. It looks like 1 is positive, 1 plus 2 is positive, and 1 minus 2 is negative, then positive times negative is negative, so, the slope on this interval is negative. On the interval between negative 2 and 0, we can pick up negative 1. And plug into f prime of x, and we have here, equals 3, and it is the positive. Negative 1 is always negative, negative 1 plus 2 is positive, and negative 1 minus 2 is negative, then negative times negative is positive, so, the slope on this interval is positive. And when x is less than negative 2, we can pick up negative 3. And plug into f prime of x, and we have here, equals negative 15. Negative 3 is always negative, negative 3 plus 2 is negative, and negative 3 minus 2 is negative, then negative times negative is negative, so, the slope on this interval is negative. Then the slope on the left of negative 2 is negative and on the right is positive, that means the function is decreasing on the left and increasing on the right, so f has a relative minimum at x equals negative 2. At x equals 0, the slope on the left is positive and on the right is negative, so the function is increasing on the left and decreasing on the right, so f has a relative maximum at x equals 0. And x equals 2, the slope on the left is negative and on the right is positive, so the function is decreasing on the left and increasing on the right, so f has a relative minimum at x equals 2. Let's do this example. Find the relative extrema of the function f of x is 2x cubed minus 3x squared minus 12x plus 12. The relative extrema occur at the critical values. We will find the critical values from f prime of x equals 0. Okay, f prime of x is derivative of 2x cubed is 6x squared, minus derivative of 3x squared is 6x, minus derivative of 12x is 12, and derivative of 12 is 0, and we let it equal 0. Okay, then solve this equation. 6x squared minus 6x minus 12 equals 0 for x. It is the polynomial equation of degree 2. We need to factorize this polynomial into two factors. First, let's take out the common factor of the coefficients of each term. It would be 6. So we would have 6 times x squared minus x minus 2 equals 0. And then factorize x squared minus x minus 2, we have x plus 1 times x minus 2. So we have the product of two factors x plus 1 times x minus 2 equals 0. Then x plus 1 equals 0 or x minus 2 equals 0. X plus 1 equals 0, so x equals negative 1. X minus 2 equals 0, so x equals 2. And x equals negative 1 and 2 are the critical values. Then put them on the number line from low to high. We put negative 1 here, and put 2 here, we have 3 intervals. Then determine the slope on the left and on the right of each critical values. When x is greater than 2, we can pick 3, and put it to f prime of x. F prime of 3 is 24, it is positive. So the slope on this interval is positive. Next pick 0 from the interval negative 1 and 2, and plug into f prime of x. So f prime of 0 is negative 12, so the slope on this interval is negative. And next pick negative 2 from this interval, x is less than negative 1. So f prime of negative 2 is positive 24, so the slope on this interval is positive. Okay, the slope on the left of negative 1 is positive, and on the right is negative. That means the function is increasing on the left and decreasing on the right. And at x equals 2, the slope on the left is negative and on the right is positive. So the function is decreasing on the left and increasing on the right. So at x equals negative 1, the function has a relative maximum and equals f of negative 1. Plug in negative 1 to the function, we would get 19. And at x equals 2, the function has a relative minimum and equals f of 2 is negative 8. If we look at the graph, the function is increasing on the left of negative 1, and decreasing on the right. So the function has a relative maximum here. And the function is decreasing on the left and increasing on the right of 2. So the function has a relative minimum here. Let's take a look another example. Find the relative extrema of f of x equals 2x cubed minus x to the 4th power. Start from finding the derivative, so we have f prime of x is. The derivative of 2x cubed is 6x squared, the derivative of x to the 4th is 4x cubed, and then let it equal 0. And solve this equation, we can factorize it to be 2x squared times 3 minus 2x. Then if 2x squared equals 0, x equals 0. If 3 minus 2x equals 0, x equals 3/2. Now we have x equals 0 and 3/2 are the critical values. Then put them on the number line from low to high. We put 0 here, and put 3/2 here. And then determine the slope on the left and on the right of each critical values. When x is greater than 3/2, we can pick 2, and put it to f prime of x. F prime of 2 is negative 8. So the slope on this interval is negative. Next pick 1 from the interval negative 0 and 3/2. We have f prime of 1 is positive 2, so the slope on this interval is positive. And next pick negative 1 from this interval, x is less than 0. So f prime of negative 1 is positive 10, so the slope on this interval is positive. We see that at x equals 0, the slope on the left and on the right are positive. Which means that the function is increasing on the left to 0 and increasing again on the right. At x equals 3/2, the slope on the left is positive, and the slope on the right is negative. So the function is increasing on the left and decreasing on the right. So at x equals 3/2, the function has the relative maximum, and equals f of 3/2, and equals 27/16. And at x equals 0, the function is increasing on the left to 0 and increasing again on the right. So there is no relative extrema here. If we look at the graph, The graph is increasing on the left of 0, and increasing again on the right, and decreasing on the right of 3/2 or 1.5. So there is a relative maximum at x equals 1.5 only. Let's do another example. Find the relative extrema of f of x equals x minus 2, to the power of 2/3, plus 1. Find the derivative f prime of x, equals, the derivative of x minus 2 to the power of 2/3. We use the chain rule and we get 2/3 times x minus 2 to the power of negative 1/3. And the derivative of 1 is 0, and then rewrite in the positive power, we have this. In this case, f prime of x never be 0, because there is no the factor of x in the numerator part. The factor of x is in the denominator part only, so if the denominator equals 0, f prime of x does not exist. So f prime of x does not exist when x equals 2, then we have 2 as only one critical value. Put 2 on the number line. Pick 3 on the interval x is greater than 2, and plug in f prime of x, we have positive 2/3. So in this interval, the slope is positive. And pick 1 on the interval x is less than 2, and plug in f prime of x, we have negative 2/3. So in this interval, the slope is negative. The slope is negative on the left and positive on the right. So the function is decreasing on the left and increasing on the right. But in this case f prime of 2 does not exist, so it has a corner at this point. Then the graph is decreasing and increasing like this. So the relative minimum is f of 2 equals 1. Look at the graph of this function, the graph is decreasing on the left and increasing on the right. And at x equals 2, the graph has a corner. To find the relative extrema, we firstly find the critical value from two possible cases. F prime of x equals 0, or does not exist. For f prime of x equals 0, if slope on the left is negative and on the right is positive, the function is decreasing and increasing like this, so there is a relative minimum at this point. If slope on the left is positive and on the right is negative, the function is increasing and decreasing like this, so there is a relative maximum at this point. If slope on the left and on the right are negative, the function is decreasing and decreasing like this. Or if slope on the left and on the right are positive, the function is increasing and increasing like this. So there is no relative extrema at these points. For f prime of x does not exist, if slope on the left is negative and on the right is positive, the function is decreasing and increasing like this, so there is a relative minimum at this point. If slope on the left is positive and on the right is negative, the function is increasing and decreasing like this, so there is a relative maximum at this point. If slope on the left and on the right are negative, the function is decreasing and decreasing like this. Or if slope on the left and on the right are positive, the function is increasing and increasing like this. So there is no relative extrema at these points. All of these are possible cases for the relative extrema by using the first derivative test. Another technique we use to test for relative extrema is the second derivative test. After we have a critical value c from solving f prime of x equals 0, or does not exist, we find the second derivative and plug in c to f double prime of x. If f double prime c is greater than 0, f of c is a relative minimum. If f double prime c is less than 0, f of c is a relative maximum. But if f double prime c equals 0, or is undefined, we need to use the first derivative test to check the relative extrema. Let's do this example. If f is 3x to the fourth minus 4x to the third minus 2, we have f prime of x is 12x to the third minus 12x squared equals 0. Factorize this polynomial, we have 12x squared times x minus 1. So we have x equals 0 and 1 as the critical values. Next find the second derivative, f double prime, and equals 36x squared minus 24x. Then plug in two critical values 0 and 1 to f double prime. We have f double prime of 0 is 0, so the second derivative test cannot determine the relative extrema. And f double prime of 1 is 12, which is greater than 0, so f of 1 equals -3 is a relative minimum. To determine the relative extrema at x equals 0, we need the first derivative test. Let's consider the number line, put 0 and 1 on the line, find the slope on the left and right of 0, we have both are negative. So there is no relative extrema here. If we look at the graph has only relative minimum at x equals 1. In the previous topic, we learned about the idea of a relative extrema. In this topic we are going to talk about a related concept known as the absolute extrema. For the relative extrema, we consider in a small interval at which the derivative is 0 or does not exist. Each function has relative maximum, or relative minimum, or neither. For the absolute extrema, we consider in a closed interval I. The absolute minimum is the smallest value in the entire interval I. And the absolute maximum is the largest value in the entire interval I. The absolute extrema may occur at the endpoints of the interval I, or at the critical values within the interval I. Let's consider this function in the interval AB. A and B are the endpoints of the interval. C1, C2 and C3 are the critical values in the interval. The relative maximum and minimum are located at the critical values. If we compare the values of the function at the endpoints A and B, and the critical values C1, C2 and C3, f of C1 is the minimum value, and f of B is the maximum value, in this interval. So we call f of C1 is the absolute minimum, and f of B is the absolute maximum. The absolute extrema may be located at more than one point if they are the same value. Okay, let's practice this example. Find the absolute extrema of f equals x cubed minus 3x plus 2. Over the closed interval -2 and 3/2. We start with finding the critical values from f prime of x. It equals 3x squared minus 3, and we let it equal 0 to find x. Take the common factor 3 out, we have 3 times x squared minus 1. And x squared minus 1 is factorized to be x plus 1 times x minus 1. So we have x equals -1 and 1 are the critical values. And the endpoints are -2 and 3/2. We will find the values of f at the critical values -1 and 1, and the endpoints -2 and 3/2. f of -1 equals 4. f of 1 equals 0. f of -2 equals 0. And f of 3/2 equals 7/8. Compare three values 4, 0, and 7/8. We see that 4 is the maximum value. So 4 is the absolute maximum at x equals -1. And 0 is the minimum value. So 0 is the absolute minimum at x equals 1 and -2. Okay, to find the absolute extrema, we just compare the values of the function at the critical values and the endpoints. The largest value is the absolute maximum. And the smallest value is the absolute minimum. Let's do the example in business. In business we need the minimum cost, maximum revenue, and maximum profit. For this example, if the total revenue in dollars for a firm is given by R of XX equals 8,000 x minus 40 x squared minus x cubed, where x is the number of units sold per day, x must be positive integer or 0. If only 50 units can be sold per day, so the maximum number of x is 50. So we will consider x only in between 0 and 50. Find the number of units x that must be sold to maximize revenue. And find the maximum revenue. Okay, let's do it. The function is the revenue r, then find r prime of x, equals 8,000 minus 80x minus 3x squared, and let it equal 0. It is factorized to be 40 minus x times 200 plus 3x. And then we have x equals 40 and -200/3 as the critical values. But x is positive integer, we can ignore the negative number. Then find the values of r at 40, and the endpoints 0 and 50. We have r of 40 is 192,000, r of 0 is 0, and r of 50 is 175,000. The largest value is 192,000 at 40. So the maximum revenue is $192,000 if they sell only 40 units per day. For this example, if the total cost function is given by c equals 1/4 x squared plus 4x plus 100. Find the number of units which produce minimum average cost per unit and find the minimum average cost. From the total cost c, we find the average cost c bar which equals c divided by x, so x must be greater than 0 only. Then we have this, and divide each term by x, we have x over 4 plus 100 over x. To find the derivative of this function, we have to rewrite the last term in power function like this. Then the derivative of the average cost is 1/4 minus 100x to the power of -2. Or 1/4 minus 100 over x squared. To find the critical values we let this equal 0, right, but we have to rewrite again in the fraction form. Then we have the numerator x squared minus 400 equals 0, and then factorize to get x minus 20 times x plus 20. Then x equals 20 and -20, but x is positive only, then x is only 20. And then calculate the average cost at 20, we have 14. So the minimum average cost is $14 per unit at x equals 20 units. And this example is about maximizing the profit. Suppose that the production capacity for a certain commodity cannot exceed 30. If the total profit is given by P equals 4x cubed minus 210x squared plus 3600x minus 200 in dollars. Find the number of items x that will maximize profit. From x cannot exceed 30, so x is between 0 and 30. Okay, let's find the marginal profit P prime of x, which is equal to 12x squared minus 420x plus 3600. And let equal 0 to find the critical values. We can take 12 out of all terms, we have 12 times x squared minus 35x plus 300. And then factorize x squared minus 35x plus 300, we have x minus 15 times x minus 20. Then we have the critical values 15 and 20. Then calculate the values of the profit at the critical values 15 and 20. And the endpoints 0 and 30, we have P of 15 is 20,050. P of 20 is 19,800. P of 0 is negative 200. And P of 30 is 26,800. We can see that 26,800 is the largest value. So the maximum profit is at x equals 30 units and equals $26,800.